In this video, we consider a different kind of quantum computing model. This is called adiabatic quantum computing. So far, the model that we have been considering is the quantum gate model, which is the most common quantum machine learning model. But this model that we are considering now, adiabatic computing, can give advantages in certain cases, at least in the near term, when the quantum gate models are not large enough. Quantum gate models correspond to the classical gate models, which classical computers have. In adiabatic quantum computing, the computation is done by a slow evolution of a quantum Hamiltonian. And the solution of the problem that we want to get is encoded in the ground state, that is the state corresponding to the minimum eigenvalue of the Hamiltonian. If we consider a quantum system which has a time-independent Hamiltonian H, then it evolves in time t as d by dt phi t is equal to minus I h phi t, where phi t is the state of the quantum system at time t. Its solution, if the initial state at time t is equal to 0 is phi 0, is given by phi t is equal to e raised to minus h t phi 0. From this, you can see that if the initial state phi 0 is an eigenstate of the Hamiltonian H, then the system at any time t greater than or equal to 0 will state in that same eigenstate, although it may be multiplied by a phase. If the quantum system has time varying Hamiltonian, then its solution is much more complicated. And if the state at time t is equal to 0 is phi 0, the state at time t is equal to at time t given by phi t is given by tau exponential minus I 0 to t h tau deta multiplied by phi 0, where this tau, this is something that you usually don't see in differential equation. This is a time ordering term which is coming because the Hamiltonian at any time t may not be commuting with each other. For such a time varying Hamiltonian system, there is an adiabatic theorem which we are going to exploit in adiabatic computing. In this theorem, if the Hamiltonian at time h at t is equal to 0 as 0, and the system starts in the ground state phi 0 0 of S0, and the Hamiltonian with time ht is varying slowly, then at any time t, its state will be the ground state of the instantaneous Hamiltonian ht at time t. So which that ground state we can know by phi 0 t is the ground state of ht for all time t from 0 to capital T, which we are going to specify what it is going to be. Now, suppose Hamiltonian is changing with time as follows. It is ht is equal to 1 minus s h naught plus s h1, where s is t by t, and this t is varying from 0 to t. And we want to, via this computation, solve a problem, get the solution of a problem. The way we would do it is we'll start in ground state of a Hamiltonian H naught, which is easy to prepare ground state. And H1, we are going to choose the Hamiltonian such that its ground state is the solution of the problem that we want to solve. Then using this adiabatic theorem, if this Hamiltonian is changing like this, at time capital T, the system is going to be in Hamiltonian H1, and because of this, its state is going to be the ground state of H1, which is providing us the solution of the problem of interest. This is how we can solve a problem via adiabatic computing. Now, for using this adiabatic theorem, there are a few conditions that are required. That is the initial Hamilton H1 and the Hamilton H1, the final, they do not commute with each other. So this is one condition. And second condition is that the spectral gap, delta S at time S, which is defined by E1S minus E0S. E0S is the eigenvalue, the lowest ground state eigenvalue of HS. This E1S is the next higher eigenvalue of HS. This spectral gap and its minimum is denoted by delta and min S, delta min. This should always be strictly greater than 0 for the whole time that we are running the system. So these are two conditions that are needed for adiabatic theorem to hold. Not only that, one more condition that one needs is that the ground state that we are talking about, in which we are going to start, should be non-degenerate, which means that the eigenvalue corresponding to this ground state should have the eigenspace with dimension 1 only. And the capital T that we are talking about should satisfy this condition. Capital should be greater than mod of phi 1s dhs by ds phi 0s in inner product mod of that divided by delta min square, which is the minimum of delta s over the time of interest. So we have to run this system up to time t, which is greater than this. If this happens, then at time t, the state, the system is going to be the ground state of H1S. And throughout time from 0 to t, the system will stay in the ground state of the corresponding Hamiltonian at that time. Now we'll see how we can use this adiabatic theorem to solve our problems, as we have just mentioned above, that H1 should encode the solution of the problem of interest. Suppose we want to minimize a function h. So this is a function with the domain 0, 1 to the power n. So z, it's a function on z, which are n-dimensional binary functions. So there any function, could be any function on this domain. We want to find the global minimum of this function. We are not assuming, making any assumption of h. So this is the problem. This is a very general, important problem of practical interest that comes up very often. So how we are going to solve this? The H1, the final Hamiltonian, we are going to denote by this expression sigma z over all 0, 1 n at z, vector z, z h zone. If you take this H1, then the ground state of it will be the value of z at which h takes global minimum, right? And this is what we want for H1 to be. Initial state, initial Hamiltonian H0, we are going to take it sigma j is equal to 1 to xj, where xj is the poly z, poly x on qubit j. So notice there are n qubits where we are working with. Xj will be the poly x on the jth qubit and I on the rest of them. So we take H0 as this Hamiltonian. It's easy to prepare. The ground state for this, which we are going to denote by phi 0 at time 0, is given by this state. This is the uniform state of all these states. And again, it's very easy to prepare. Interpolating Hamiltonian at any time t, we are going to take as hs equivalent minus h0 plus sh1, as we have mentioned earlier. So we want to solve this, get the minimum point of this function h via this method, and the procedure as mentioned above is followed. We prepare the system in ground state of h naught as given above. We slowly vary s from 0 to 1 over time t. S is t2 by t, and t will go from 0 to capital T. Because of the adiabatic theorem, and remember, this ground state that we got is non-degenerate, that we can easily see. So by the adiabatic theorem, as the system evolves at time t is equal to capital T, the system will have a Hamiltonian H1, and it will be the ground state of that. And that ground state is the global minimum of this function small h, the way we have just prepared. So this is then a way from adiabatic computing to find the global minimum of any arbitrary function on binary vectors. What is the complexity of this? We have to run this up to capital T, which is proportional to 1 by del min square, as we have defined above. For many NP hard problems, because these are like optimization problems in binary sequences, delta min, where t is corresponding to this, shrinks exponentially with size, and that means as n, the size of the problem increases, this capital T will exponentially increase. Therefore, for large n, this can lead to, in practically, large evolution time. However, even with this, it has been found for many practically important problems, the capital T that we get here is much, much smaller than the time required for the classical computation. So this is the benefit that we get from adiabatic computing, even with scale. Another thing is this adiabatic quantum computing that we have just given is computationally equivalent to the gate model under sufficient runtime. Runtime is that time we are taking this. What it means is the following. If gate model can compute any function, then adiabatic quantum model can also compute that function. And we know that gate model can compute any function that a classical computer can compute. Therefore, AQC is also universal in computations. Secondly, if a problem can be solved in polynomial time via gate model, via AQC as well, it can be computed in polynomial time. One of the advantages of gate model and the adiabatic model is currently the gate computers that we have, quantum gate computers that we have, are not very large. And therefore, you can't solve interesting large problems via the gated quantum computers. However, some of the problems of scale of interest in practice can be actually computed via the adiabatic quantum computing model that we have just described. And therefore, at the moment, this is an important quantum computing model. So as a special case, we give Grover's algorithm problem that we solved earlier via the Grover's algorithm in gated model via adiabatic quantum computers. In this case, H0, the initial Hamiltonian we are going to take as before. H1 we will take as I minus vector M. Now remember, what is the Grover search algorithm? We have capital N elements, and we are searching for one particular M element, which we are going to denote by M in this capital M. How to search it? In classical case, you have to use search for of the order of N, capital N, right? But via Grover's algorithm that we have studied earlier, we need to use square root of n order searches. Now, via this adiabatic thing, we are showing the same problem can be solved in the same runtime of square root of n as follows. H naught we take as before, H1 we take as this. If you do this, then if Hz is 0, then in this case Hz is 0 if z is equal to m and Hz is equal to 1 otherwise. So the search problem that we are talking about here has to search for one particular element m, and to do that we define this function hz as hz equals 0 if z is equal to m and is equal to 1 otherwise. So therefore at z is equal to m, this has a global minimum. And now we use the previous adiabatic algorithm that we have mentioned to get the global minimum with this. So which can be done by taking h1 is equal to I minus this m adjoint m. And you can see that this ground state is going to be the minimum get delta min that we have defined above. In this case, occurs at s equal to 0.5. So therefore, at 0.5 time, uh, we have to run this algorithm for that much time. And this gives the runtime of 4 square root of n, which matches the Grover's complexity in the gated model. So this is another important application that we have just mentioned and matches the complexity of the gated model. Now we consider a modification. Rather, instead of a modification, this is another quantum algorithm which is inspired by the adiabatic computing that we have just talked about. It is called quantum approximate optimization QAOA algorithm. This is a hybrid quantum classical algorithm. So the variational circuits, quantum circuit that we have talked earlier. So this is that kind of algorithm, but it is motivated by the adiabatic, as we are going to uh, explain now. So you start with ground state of H naught. So again, this is this Hamiltonian we are starting with. And here you take this, the Hadamard base, and there are n qubits. So you start with the state. We consider P positive integer, whatever you fix. And then we take parameters gamma which has P components, gamma 1 to gamma P, another vector beta with P component beta 1 to beta P. Corresponding to these parameters, we take the operators exponential minus I gamma k h1 and exponential minus I gamma beta k h0 and apply this variational circuit on this initial state. So we start with this initial state and we apply this variational circuit on it to get this state, which we are denoting by phi gamma beta. And after applying this, we take measurement of the state with respect to H1. Remember the H1 that we have given above, which corresponds to which has the ground state, which corresponds to, let's say, the minimal value of H function that you want to optimize. So the expected value of the measurement via this is EP gamma beta. So it does depend on the parameters gamma and beta that we choose here. We compute this by making repeated measurements over this and then find gamma beta parameters which minimize this quantity. And this minimization we can do via the classical methods. The idea here is that at this minimal value, the state that we are going to get at this point, this will be close to the ground state of H1 Hamiltonian that we have considered earlier. And remember, ground state of H1 is the state corresponding to the solution that we are seeking. So what we have done is, instead of using the adiabatic method, here we are taking a variational circuit method, but motivated by that. We considered H0 and H1 as given before, and these parameters, and use this variational circuit to compute this. How this thing comes is, this comes from the inspiration that we get from the adiabatic computing. And we explain that briefly right now. Um, Remember, if we have a quantum system with variable Hamiltonians ht, then a state as time t, phi t, psi t that we have taken is given by this. Now, we can take this overall time that we are considering, let's say, if we are considering from 0 to capital T, and then at t is equal to capital T, this is the state going to be. This exponential that we get, we discretize it by taking time discretization of the overall time. We can, in that case, show if this ht is given by this with h0 and h1 fixed, then this integral, exponential of this integral, can be given in this form. If the time axis has been split into p intervals. So the adiabatic computing method that we have given there can be approximately written as with its state at time t in this form. And if we ran this capital T up to whatever that we mentioned here, then at the end we were going to be in state H1. Now, what we are saying is, we are not necessarily going to run it up to that capital time t. It can be some smaller time. Why? Because it is possible that that capital T for which you have to run the adiabatic computing algorithm can be too long of time, right? As we mentioned, it can increase exponentially with n. So instead of doing that, motivated by that algorithm, we use this variational circuit and take these parameters which minimize this. Then the state that we are going to get here is going to be close to the ground state of H1 that we have, and H1 ground state is the solution. Therefore, this state may not be the solution of the problem that we are talking about, but it will become close enough to that if this expected value is small. And in this algorithm, as against the adiabatic algorithm, we have not done the computation for necessarily a very long capital T time. So we summarize these properties of the AQ2A or A. It does not require long adiabatics evolution and corresponding to the minimal spectral gap. But if the number of terms P you take larger, the approximate solution that we get at the end will improve with P. As I said, Robert's algorithm is a special case of this, and particularly in the NISQ, noisy intermediate scale quantum situation that we are right now, when the quantum gate systems are quite noisy, and their noise-free versions are very small. In that case, this particular algorithm can be very useful. However, there are challenges. Getting the minimum spectral gap can be difficult. So this is again the issue with the adiabatic problem. In this algorithm, we are not talking about that. So this is another advantage. Also, the ground state degeneracy can happen. We mentioned that the adiabatic theorem holds if the ground state is non-degenerate. If it is degenerate, then there can be issues. There are efficiency comparisons between AQC and gate-based systems, and those depend on the problem and the hardware. And the theoretical relationship between QAOA and adiabatic evolution is still not very clear, and it's an open area of research. So in last 3-4 videos, we have been talking on quantum machine learning. So how we can get quantum machine learning algorithms from the algorithms that we have talked about here, we comment on that right now. Both AQC and QAOA can be applied to optimization tasks in the machine learning. Remember, in machine learning, often we have to get parameters which will minimize the loss function. So this loss function minimization problem can be addressed by the adiabatic computing and QAOA, because in both of these cases, we have given the examples of how some functions can be minimized via this method. And often you can get advantage, computational advantage compared to the classical methods. So these loss functions can be optimized by these methods in a more efficient way than the classical case. And examples are object recognition in images, neural network trainings. People have trained neural networks via QAOA and AQC, and that can be done more efficiently than in the classical way. And of course, you can solve many combinatorial optimization problems in machine learning via this method. Thank you very much.